hide this. Okay. So do you see my screen now?
Yes.
Yes. So let's get started. This is now chapter 14 of your course book. By the way, we have time, I will try to provide you more details about your final exam. I know some of you are concerned. We covered a lot of material, how the exam will look like. My suggestion is look for the previous exams and also try to see the questions at the end of your course book. So that will give you a very good idea. Also, if you see some previous exams, you will see that if I ask you something about an architectural style, I usually provide you the diagram of that architecture. So, so that you don't need to really remember a lot of stuff. Okay. But it is good that you go through the course book at least 1 or 2 times, read these chapters, and that would be good enough for you to excel in your exam. More details will come. Okay, so event driven architectural style, it's very much popular these days, and it's a modern architecture. It's a distributed one, so let's get started. So event-driven architectural style is a distributed asynchronous style architecture, and it is really popular these days. And why it is popular? Because it really support scalability and performance. So modern applications can rely on this one. There are many other options also, but this one can be one candidate you can think of when you need scalability and performance. So it relies, as we said, it relies on asynchronous communication, which means messages, can proceed independently without waiting for the responses. So in asynchronously, you just send the messages and you do other things in your architecture, in your software. And whenever those messages are being processed or whatever invocation it required, whenever it happened, uh, it is completed, it will come back to you. The pointer will come back to you. So what it happens with that kind of asynchronous communication, what you immediately get is the responsiveness of your system. It is very important to remember though that responsiveness does not mean fast processing. Responsiveness is just like you call me, hey Muhammad, and I immediately say yes. And then you say, can you do me this? And I have these pointers for you. And I say, hold on a sec, and I'll come back to you. And then another student calls me, hey, I have a question. And I say, yes, please. And he says, I need this. And I say, hold on a sec, and I will come back to you. Give me just one moment, please. 1 second, please. So what I was saying is that um, responsiveness does not mean fast processing. Responsiveness simply means that system will respond to you quickly. So it gives you feeling of fast processing. We will talk about it a bit more in afterwards. So it can accommodate applications of various sizes. That means it supports adaptability and flexibility within your architecture. And if we talk about the vocabulary or the phrase or the words we use in event-driven architectural style, these are like events. So events are being triggered for actions. So whatever in event-driven architectural style happens, it happens in response to some event that occur within your system. So you identify important events for your application, and your system respond to those events. Okay. So these events can be initiated by user, it can be initiated by system, it could be initiated by internal processes. And then you have event processors or services. Okay, consider them components. So these components react and process events. So an event happens, so you can have many event processors, and one of them or maybe two of them, depending on how you design it, will respond to that event. Okay, process it. So or react to that. And then we have event brokers. So event brokers are like, distribute. What event broker does, as the name broker suggests, it simply distribute events to relevant event processors or services. Okay. And then we have mediators. So mediators controls the workflow of your events. So which event should happen first, which event should happen next. So that kind of control is with mediators in our event-driven architectural style. So it enables features such as error handling and recovery if something goes wrong. So this is a traditional request-based model. So far, we are familiar with this kind of model. Okay. So most of the applications follows this. In that, what usually we have some kind of, request processors, and number of request processors you can have just to have, if it's a domain driven design, they can correspond to different functionalities provided by your system. And if it is, let's say, just for the purpose of scalability, you put them in parallel, then it could be about the same thing, but a few requests goes here, some, and when it is overloaded, you can go here and so on. So all this kind of possibilities exist. So the request comes to this orchestrator. As the name suggests, it's an orchestrator, orchestra. So this orchestrator controls uh, the request where it should go, to this one, to this one, or to this one. So this request orchestrator can be implemented like a user interface. It could be an API layer, or it could be a service bus. Okay. So it is the responsibility of a request orchestrator to deterministically determine the request should send to this one, or this one. So this is the traditional flow of within any application. So if we look at some example, like, customer requests their order history from the last 6 months. So request comes in, and then what happens? So you get some kind of request state, and then um, this orchestrator will decide whether to send this request to this processor or this processor or this processor. Whoever processes it, then it may require fetching something from database. It will give back a request state here, and then that request will be fulfilled. So in contrast, if we talk about event-driven architectural style, so in event-driven model, what happens? So you got events, okay? So your system actually reacts to the events and take actions against them. So this is a flip or different kind of mindset you need to think of when you are looking at event-driven architecture. Your request is like, some events happen, and the system responds back to take some actions for those events. So here is an example, like submitting a bid for a particular item within an online auction system. So submit bid could be an event, okay? And now it is not a request, but an event. And it happens after. So these events, of course, happen within some order. Like, when the current asking price has been announced, one event, then afterwards, this event submitting a bid can be initiated. So when this event is initiated, then your system will start taking bids from users. And then the system must respond to this event by comparing, like, let's say you bid, I bid, many people, has been bidding. So it is the responsibility of the system to look at all these bids and keep track of them and find out, keep comparing them and find out who is leading those bids. So putting them on top. So finding out, the current highest bidder. So this is how an event-driven architecture based system work. So you got events and your system or event processors respond to those events in some order. So you can implement event-driven architecture in two ways. So there are two structures or topologies that you can have in an event-driven architectural style. One could be broker topology and another one could be mediator topology. So in broker topology, what it does, it supports a high degree of responsiveness and dynamic control. So for instance, if I just try to give you a rough idea about this diagram, you got many event processors. So event processors are computing components, okay? And what we also have is kind of channel, event channel. And this event channel is being broadcast all the time. So an event starts, an initiating event actually start the whole reaction or chain of events, and it is put in this event channel. And now it is being broadcast. So it is being broadcast, so all these events will listen to it. So, but this event that you put into the event channel, maybe it is only this event processor that must respond to this event. So this one will process it, and then after processing puts it back the new result or the next event in the event channel, and now it is again being broadcast. All of them are listening, but maybe it is only concerned by this event processor, so it will take it, process it, and then if there is something more to put in back in the event channel, the next event, it will put it back. And then it will be again broadcast, and all the events processors will listen to it, and whoever should respond will respond. So this is how broker topology works. So it supports high degree of responsiveness and dynamic control. So control is really dynamic because there is no central control in this one. Everyone knows what they should do. As opposed to, we have a mediator topology. Here, in this one, we have control over the workflow. Who does what? Who will process the first event? Who will process the second event? Mediator mediator topology will instruct those event processors to do certain process, certain events. We will see that in detail afterwards. Okay. Coming back to broker topology first. Here the message flow is distributed. As you can see that all this communication, by the way, the dotted arrow here shows that it's an asynchronous communication happening. So it's also distributed across event processors, and it's like a chain reaction in broadcasting. Okay. And what we need is usually a message broker over here. And we have many message brokers like this one. You can use RabbitMQ, you can use ActiveMQ, you can use HornetQ, and it is useful for relatively simple event processing flow. In this one you don't have any event orchestration. So orchestra, we know orchestra. As you can see that consider all these people who are playing some kind of instrument, they are event processors, and they all are listening to you know this person here. So that is orchestration. Everybody knows when they should respond to the instructions or events happening through this man standing here. So there is so in that I see. So I said it opposite. Yeah, it is not, they know what they're supposed to do. They don't need to listen to it. I should not have put this line here. Sorry for that. So no, it's not this one. It's the mediator that depends like this one. Everybody is being instructed by this man. But in this one knows what they should do. They are listening. So let's say we put an initiating event here. It goes to the event channel, and now it has been broadcasted. And when it is being broadcasted, what happens? Everybody listens. This one listens, this one listens, listening, listening, and listening. But it turns out, so all these where I put threes, they listen to it. But it is only this one that must respond. So this event processor knows that this kind of event should be processed by me. So this event processor processes it and generates a new event, put it back into this event channel. Now it is back into the event channel, again broadcasted. And when it is again broadcasted, now again it is listened by everyone. So it is listened by this, it is listened by this, it is listened by this. I try to show that through these 4 points, and it is even listened by the one who just put it here in the event channel. And now let's assume it is this event processor that must respond to this kind of event that was put in here. So now it processes it and then afterwards puts it back here in the channel. And now again, everybody listens. This one is listening, this one is listening, this one is listening, again, this one is listening, and this one is also listening. Five here. So all those are listening, and whoever should respond to this new event will respond. So this is how this works. So let's go through one example. So here is a book purchase example. And as you can see that it's a typical retail orders, you assume that you got a typical retail order system. First thing I want you to notice is that you got one event processor for order placement, another event processor for warehousing, one event processor for inventory. You got one for payment, you got one for notification, one for order fulfillment, and so on and so forth. So what it tells us that all these event processors within an event-driven architecture style, depending on broker topology, are highly decoupled. They are independent. Order placement only happens here. Payment only been processed here. Inventory only processed here, and so on and so forth. This is the first thing we should notice, that using broker topology and event-driven architecture, within an event-driven architecture, event processors are highly decoupled and they are independent from each other. Now, what happens is that since they are independent from each other, if there is too many processings, payment processings done by this, and it is kind of becoming a bottleneck within your system, you can scale it. You can give more compute, you can add more, similar shadow payment systems and so on and so forth. So you can scale it up, scale down. So you can do using load balancing, you can scale up and down each and every component separately. This is very important. Okay, now so because these are decoupled, so also you saw that even in this, it's more like a publish, subscribe, or fire and forget kind of topology here. You fire it, you just make an announcement, and then you forget about it. And all these were listenings, whoever should respond will respond. So there is a lot of uh, trust on the system that whoever should respond will respond. So because of this reasoning, publish and subscribe messaging model is much more, makes more sense in this uh, broker topology for event-driven architectural style. So let's go through how things are processed in this example. So we are here. We purchase this book, Software Architecture, a Modern Approach. And this event is being initiated. So this is the initiating event, the starting point of our process. and we place that into our event channel. So place order is the name of that event, which is now waiting in the event channel. And of course, there are multiple people, many people, purchasing different books. So there is a queue here. Though it's a publish and subscribe, but still it's a queue. Whenever the turn appears for this place order of purchasing book, it will be uh, published. So then this order placement supposed to listen to it. So everyone is listening, by the way. I just show that through these ears. Everyone is listening to these uh, broadcasts. All have been subscribed. So if we talk about from the perspective of, like YouTube or Facebook, all these are listening because they have subscribed to the channel, this one. But then it is the order placement who should respond to place order. So this responds to it, processes it, okay, and then generates a new event, and its name is order created. And order created is again being broadcast. Everyone listen to it, but it is only the responsibility of three components where I put three, this one and this one that must respond to it. So for instance, payment should process payment for this order created. And the answer could be two possibilities. If the payment is successful, a new event will be generated, payment applied, and put it back into event channel. If payment is not successful, a new event will be generated, payment denied, and put it into event channel. At the same time, by the way, these three things are happening independently from each other. Either they should happen all together, or by the way, we don't have that control here for the moment. We will talk about it in a minute. So then at the same time, in parallel, inventory should work on this order created. And then in this event processor, inventory will be updated. So since inventory is updated, maybe it generates an event called inventory updated and put it back into channel. So this payment processor either will add this payment denied or event or payment applied event. Similarly, this notification channel will see that, sorry, this notification event processor or service will see that an order is being created. So it will generate an email back to the customer that we have created your order or something like that. Then let's see what happens in the case of payment applied. So when you go here, okay, so payment applied and here inventory updated. So this one is listened by all of them, but order fulfillment is the one who will respond to it. So then it will apply the payment and then it will generate a new event order fulfilled and put it back into channel. At the same time, here inventory, so here this inventory updated is waiting, we will talk about it in a minute, but as you can see that inventory updated will be listened by warehouse and it will see how many inventory has been sold. So it will ask for resupplies through the event inventory resupplied. So it will generate this event maybe on some console so that we know which further items needs to be bring back to our warehouse. Now, if the so let's say first let's go through the process when it is a success, it is a successful payment. So order fulfillment has put this order fulfilled, and then this will be listened by shipping, and shipping will take the order, process it, and then once it is done, it will generate an event order shipped. So that's an event that now order has been shipped. And then this order shipped event is listened by the notification service. So notification now will send an email to user or to the customer that your order has been shipped. Now, if we go back on this part, so when the payment denied, what will happen? We come back here. By the way, look here, when order was fulfilled again, it was listened by the notification. And at that point also, we sent an email uh, to the customer. So we sent emails when the order was created, when the order was fulfilled, and when the order was supplied. In case of when the payment denied, over here, again, we do nothing further on this side. It's only the notification that that sends and generates an event email sent, and by that email, it is told to the customer that your payment is denied. So that is a broker topology in action in publish subscribe fashion for an event-driven architecture implemented for a typical retail order entry system. So what are the trade-offs of this broker topology? Some advantages and some disadvantages. Advantages are really easy to understand. Highly decoupled event processors, high scalability, responsiveness is there, performance is there, fault tolerance is there. Why fault tolerance is there? If this one becomes faulty, it is easier to replace this one or have another shadow component, and we just wake that up and the whole system keeps working. Performance is high, responsiveness is there, scalability is there, and decoupled environment is there. However, there are some disadvantages. The first one is there is no workflow control. So that means there is no centralized control to monitor when the entire transaction is completed. Nobody knows, as you know. Everyone is doing their own stuff. And there is no one who has a holistic view of the whole system. Okay, that is something we need to work on. So there is no centralized control. And then system, because there is no centralized control, error handling becomes very difficult. Why? Because the system is unaware of failures. When the payment processor crashes, then what should happen further? If this one is crashed, now all the other, though decoupled, it's still a business process depending on this payment. So how do they know that they also must stop? We don't know. So that is the problem, that if some service or event processor goes faulty, how do we know that? We will be unaware of failure. So error handling is different. Recoverability is different because of the same reason. And then also, let's say if one of the event processor gets stuck due to some reason, how the others ones will know? There is no way. You see? So if one business process gets stuck and unable to move further, so we need, some kind of manual or automatic intervention. We need someone looking at the system all the time. We need some dashboard. We need something so that we keep checking our system for the correctness of the business. So it is not easy to restart or resubmit the failed transactions. If some transaction been failed, then it would be really hard for us to restart it or resubmit, because let's say someone passed through and then here we got stuck. How do we restart? It's not clear in broker topology for the event-driven architecture. And finally, no component tracks or owns the state of the original request. Everybody does what they're supposed to do. So there is no holistic, track of the original state. That makes it really difficult to resubmit or restart. Now let us consider the other options. So we talked about broker topology. Just remember what we talked about. We said that broker topology, there is no central control, and it's more like publish, subscribe kind of communication. In mediator topology, we have a lot of control, and that is why it addresses some of the shortcomings of broker topology. So in event mediator, as you can see that, by the way, what we have, we got, in a mediator topology, we have initiating event, we have event queue, we have event mediator, we have channels just like before, and we have event processors, all that. But it is the task of this event mediator to manage and control the workflows for initiating events. So this event mediator knows which event should send to what event processor. Okay. So mediator topology mediates what event should go to which event processor. So let's see event mediator topology in action. So what it will happen is that first here events are being initiated, and then put it in this event queue. And when it's their turn, it will be processed by an event mediator. So this event mediator sends it to, so by the way, this event mediator knows where this event should go. So let's assume that one should go here. So it will put it in this event channel, and when it's done, it will be processed by this event processor. So this event processor is not listening now. This event processor is just uh, fulfilling the request sent through this event mediator. So in contrast to broker topology, um, there is no broadcasting here. It is just, this event mediator know where to send a request. So we can have multiple mediators. As you can see that we only have one mediator here, and that could be a single point of failure. We can also have multiple mediators in that topology. So we can have, for instance, one mediator for customer mediator. It will be responsible for events like new customer registration, profile update, and so on. Or we can have some mediator like order mediator, and it can be responsible for like adding item to shopping cart, checking out, and so on. All the things related to order activities. So what happens is that through this introducing, multiple mediators, we are reducing the single point of failure, which is pretty common issue with this mediator topology. As you can see here, if this mediator goes down, the whole system will go down. So having multiple mediators can solve that issue, but also it increases the throughput and performance, because now this will not become a bottleneck with a lot of requests being processed by this mediator. So it will increase the overall throughput and performance also. You can implement an event mediator, in multiple ways. So you can have a very simple mediator like a simple event mediator. It's more like a code you write in Java or C Sharp. So for simple error handling and orchestration, as we said, it's like this one, everyone is listening, everyone is actually looking at this event mediator, and this event mediator sends things to whoever is responsible for that. So it could be that kind of rules implemented in, for instance, Apache Camel, Mule, ESB, or Java Spring integration. And it would typically be some code written in Java or C Sharp or in some other programming language. Then you can have complex event mediators, and it requires conditional processing and multiple dynamic paths. So that complex error handling services or directives could be implemented. So for that, if you want a complex event mediator, you can use Apache ODE or Oracle Business Process Manager, Oracle BPEL, Business Process Execution Language. So usually these frameworks, they support an XML-like structure, and in that you write your logic. And then you can have hard event mediators. Hard event mediators require human intervention. So it's more like you can intervene when the processes are happening. So if for event flows requiring long running transactions involving human intervention, throughout the event process, we can have hard event mediator. And in that scenario, you can use a business process management engine like JBPM uh, to support this kind of mediation. So let's see in this diagram, it's just shows how a delegation of different events can happen within your system. It's an extreme example. We assume you have all these mediators within the system. So you got simple mediator, you got complex event mediator, also you got hard event mediator. So it's just it's a generalization of it. So in the beginning, as in any event-driven architecture, an event is initiated, put it in the queue. When it's turned, it appears here. And then this single event mediator, based on the type of this event, will decide whether it should send to some processing uh, event processor to process it over here, or it is something that should go to maybe complex event mediator, or maybe go to hard event mediator. So this simple can event mediator cannot make this decision. So it passes just whether it should send it to hard event mediator or it should send it to complex event mediator. And when that process, so an event is initiated here, process, I mean, this mediator either sends it to this event processor or further redirect it to this one or this one. So this is a hard event mediator that requires human intervention, and this one depends on some complex business rules. And then this one will decide whether that event should be processed by this event channel or this event channel. And if you look at this hard event uh, mediator, then through human intervention, it will be decided whether this event should go to this event processor or this event processor. So now we are going to look at an example where we will see mediator topology in action. So let's see. So it's an retail order entry system. So an order has been placed, the same example we saw before. So here, step number one is order, place order. And in that step, we will create an order. In step two, process order event will be initiated. And in that, we do three things in parallel. So email customer that order has been placed, apply payment, and decrement inventory. So it is very much similar to what we were doing in this example here. It is the same example that you see here. Now we want to do this example through mediator topology. Here we saw that how it is done by broker topology. So it is the same example. So then once all these things are done, step number three happens, which is an event fulfill order. And in fulfill order, we do two things: pick and pack order, order more stock if necessary from supplier. In step four, an event is triggered ship order. And then in that, we do two things. Email customer that order is ready for shipment, and ship order to customer. And finally, notify customer. And in that, we just notify, send email to customer. And by the way, here what it is written is that these things happen in parallel. These two things happen in parallel. These two things happens in parallel. However, this step two, three, and four is happening in serial order. So first this will happen and then all these things in parallel. Then this will happen and all these things in parallel. And then this will happen and all these things in parallel. So this is what I say for that here, that events within these steps happen concurrently in parallel. However, these steps are performed serially. Okay, so number one, so purchase initiating event placed in our place order uh, queue. And when it's done, you see these are the steps. We put them here. So that this logic that this is our business process looks like happening all these steps one by one is now within your event mediator. So you implement that business process in your event mediator. And then the step one is, as you can see here, create order. That is your event. Okay. And this event is given to this order placement service or event processor. Okay. So whenever it's done. So initiating event place order is now sent to customer event queue over here, and then for further processing. Then create order. Uh, this event is generated by your event mediator, and now it is sent to this queue for which is for this order placement event processor or service. So as you can see that mediator generates a create order processing event and then sends it to order placement queue over here. And when it's done, it will be processed by order placement service or event processor. Then what happens? This order placement event, a processor accepts it, validates it, and then create an order, returning the order ID back to this mediator. Okay, this is step number one. So by the way, now it is up to this mediator, the logic you implemented here, whether this order ID should be immediately sent back to customer or wait until the whole process is completed. Depending on that, we will, whatever we implemented, order ID will be sent back whenever is its time. And then now we are in the mediator again. Now the mediator triggers three events in parallel. So email customer placed, apply payment, and in adjust inventory. So this email customer placed event is generated and put it in the queue for notification service. Apply payment is put in the event is generated and put it in the queue for the payment service. Adjust inventory is generated, event is generated and put it in the queue for inventory service. So this is what I mentioned here. And then all these happens in parallel. And then what happens in step number two, this mediator should wait back the responses from all of them. They are happening in parallel, but until all of them are completed, we can't go further. Okay. So now all of them are completed. And now we can go further. And if some error happens, let's say in apply payment, we will stop. We will not process it further. And maybe we will send an email to the customer that right here that email your processing, your payment has been stopped due to some reason. But if everything goes right, then step two is completed. Now in step three, the event mediator, after receiving confirmation from these event services, event processors, it will generate two more events. Fulfill event, sorry, fulfill order and replenish stock. So fulfill order, or let's call it apply payment. This one is placed for the order fulfillment service, and replenish stock and event is generated like order stock and put it in the warehouse queue for the warehouse processor. So now once this happens successfully, again I just talked about this event here. Okay, so here the details are still about this one. like apply payment, order payment, and everything happened nicely. And if something goes wrong, then we will stop, and then a corrective action will be taken. Now we are here, fulfill order and replenish order. So what happens? These are processed by, you know, as it is mentioned here with this one and this one. And once it is processed, done. And now the mediator knows the next thing within the steps is uh, step number 4. Two things happen in ship order. We ship order to customers, and we email customer uh, with the message fulfilled, that your order is fulfilled. And this goes to, as the mediator knows, this goes to the notification service in the queue of notification service, and this one should go to the queue of ship order service for the shipping. I mean, ship order is just the event placed in this queue for this event processor or service shipping. Once it is done, then finally we notify that your shipment is now shipped. So again, this goes to this notification service. And then we complete all our events. But here an important thing to remember is that in mediator topology, we use commands. It is a command that is given uh, to these services or even processors. It's not, you know, so it's not something just must publish and then forget about it. It's more like a command. So it looks like an event, but events are enforced through commands. We can say it like this. So a command must be processed, but event can be ignored. So this is how we can separate them. Okay. So still command is also an event for a certain service, but it should be fulfilled, must be processed by that service, whoever is assigned. So now in the trade-offs, it is now flipped. As you can see, whatever was the disadvantage in the broker topology becomes now advantage, and whatever the advantage was now becomes the disadvantage in mediator topology. You see, there is no right and wrong things in architecture. It's only the trade-offs. So now you got a much better workflow control, you got error handling, you got recoverability, you got restart capabilities, you got better data consistency. But now what are you giving up? More coupled event processors now. They are really, following one business process altogether. Lower scalability, lower performance, lower fault tolerance, and modeling complex workflows is not as easy as it looks in this diagram. So that is the disadvantage. So what I said is now just mentioned here, like we got a better workflow, state management, error handling, and compared to broker topology. And the event processors are less decoupled, as we can see, that can affect your performance, and difficult to model dynamic event flows over here. So these are, some trade-offs between broker topology and mediator topology within an event-driven architecture style. So it is now 9:54. I will complete this slide, and then we will take, sorry, 10:54. So we will take a break. Okay. So asynchronous capabilities that we have, what does it imply on our event-driven architectural style? As we know that asynchronous capabilities are, this EDA or event-driven architectural style solely, relies on asynchronous communication. And this is the unique characteristic over other architectural styles. And by the way, asynchronous capabilities allows you, it's a very powerful technique that allows you to have responsiveness of within the system. So your system will look like really, really responsive. Okay. And I will try to motivate that with this example. And by the way, you have seen that example in all these modern applications. Imagine you are posting a comment on Facebook post, or you are posting a comment on a YouTube video and things like that. So this is the scenario very much similar to that. So a user is posting a comment on a website for a particular product review. Okay, it could be product review, it could be Twitter account, it could be Facebook post or something like that. And let us assume, now I will try to give you details with this diagram. Bear with me, there is too many things, but I will explain you slowly. First of all, when you post a comment, you write your comment over here, and then you click on this button post. So this generates an event that goes to this event producer whose name is post comment. And post comment is not a very simple thing. It does many things. Okay. Because let's say it's a product review, we want to moderate. So this website is very much, careful about what is written in the comments. So it applies three things on your post when you click on post. So it checks for unacceptable word checker. Are you using some, abusive words and stuff like that? Something with unacceptable, or like abusive sentence checker. You can have that. Or also maybe you can have some kind of political rant checker. So it could be just one thing or many things, many services like that, checking different, things, political correctness, abusiveness, or threat, and stuff like that, unacceptable words, so on and so forth. So all that happens here. So that is why it's going to take, process it sometimes. We assume, uh, by the way, this does not happen on this side. This is the client side. This happens on this side in the comment service. So this one is really simple. It just, you write something, click on post, and it sends it to here. And now here you got these things implemented in this comment service here. All this is implemented, making it a bit slow. Like to process your comment within these filters, let's assume, just for the sake of this example, that it takes 3000 milliseconds. Okay. So in order to process a comment, it takes 3000 milliseconds. Okay. So we check two scenarios. The first scenario is it's a synchronous communication. So what happens then? So this event processor sends your comment, and now it is waiting here to receive back your answer. So it is now blocking. So it's a synchronous communication. So it sends the request, and now it is blocking here to go to other post or do anything further. You have to wait now. And let's say because the communication happens over the internet, for the sake of argument, assume it takes 50 milliseconds. And let's say you implemented that through RESTful API so that it goes over the internet and it takes 50 milliseconds. Then this event consumer processes the comment and it takes 3000 milliseconds. So how much? And then it has been, posted, or let's say if it is inappropriate, some messages generated, whatever the response is, it goes back to you again 50 milliseconds, because if it takes to reach there in 50 milliseconds, it will take to go back in 50 milliseconds. And now the process is released. You can go now and like another post, you can do something else, but you were waiting. And how much did you wait? 500 plus 5, sorry, 50 plus 50, 100, and 3000. So 3100 milliseconds is the wait when you click on post button and getting back the control. So 3100 milliseconds. Now compare it with asynchronous communication. So this event processor will send this comment that you wrote asynchronously. And since it is an asynchronous message, it will have in the middle um, a queue where it will be, pushed for some time. And whenever is its turn, it will be processed by this event consumer. So since we are assuming that this channel is kind of in the middle, and since it is in the middle and the total distance it takes 50 milliseconds, we are assuming that it only takes you 25 milliseconds. By the way, what happens? You click on post, so your message goes from event processor, this one, post command to this channel, only 25 milliseconds. You just waited for 25 milliseconds and you get back your control. And that could be, you get back your control, you don't maybe, now there is depends how you implement it. You can get a response like, okay, do other things and we will get back to you, or it doesn't say anything. You just post, click on post, you get back your control, you do other things. And what happens in the background, when it was time for your message, it travels to the event consumer, taking 25 milliseconds more. And then this comment service takes 3000 milliseconds to process your comment, and then finally posting it. So it took the same time, but you felt like much faster because you just waited for 25 milliseconds. So, and the system was back to you with a response. So this is what responsiveness looks like. And I just explained all that here. It still takes uh, 3100 milliseconds, but you felt like just 25 milliseconds. That is why when we have an unstable connection, what happens, sometimes, we don't see our comment being posted. We try again and again. And once everything is fine, we saw like 5 times the same comment we posted because we were communicating with the system asynchronously. It doesn't tell us something and we assume it has been posted, but it was still processing it, maybe due to some other processings or maybe some congestion. It got a bit delayed, it got rejected. So we kept posting it 2, 3 times, and once the whole processing happened, all those comments appeared on the page you are posting your message. So this is what asynchronous capabilities give you. Responsiveness, response time is much faster. Okay, let me just finish this slide and I will then stop and we will take a break on this one because it is, again, we are comparing what responsiveness is and what is performance. So responsiveness is precisely getting back to you quickly, does not mean performance. Performance of both. Here, when you made a synchronous call or when you make asynchronous call, the performance is the same. It takes 3100 milliseconds to process a command properly. Okay, so the basic concept is summarized in this line. When the user does not need any information back, why make the user wait? So responsiveness is all about notifying your user that we are working on your input and we will get back to you if something goes wrong. In and if something goes right, maybe you don't get back. It's up to you. Performance is now making end-to-end process faster. So if you want to really improve the performance, then you have to work on this part so that this service that you have can do it faster, algorithmically, adding more compute power or whatever you have to do for that. So that could be the performance, increasing the performance. Right now, Just through asynchronous communication, you got better responsiveness, but the performance is the same. So it's more like an illusion of performance that you feel when you are using a system that implements asynchronous communication. So synchronous means the user is guaranteed that the comment has been posted. So synchronous communication does that. But asynchronous only gives you an acknowledgement right now. We received your comment, but with a future promise that either eventually we will actually post it. So this is what asynchronous does. So consider but here it is important. Now I will say that you can't really use asynchronous communication everywhere, right? And here is a critical example. So consider an example where the purchase of some stock is taking place asynchronously, and then there is no way to get back to the user. How frustrated you will become if this kind of important communication happens synchronously, sorry, asynchronously. So here it's really important that such time critical events should be handled, you know, either synchronously or does asynchronous communication with error handling. And we will see that how handling can be implemented in asynchronous communication. Best way is go for synchronous communication in critical systems, but we can improve this asynchronous communication by introducing some kind of error handling. So this is the main issue, having how to handle errors, and we will see some techniques how we do that in the coming slides. So here now I will take a break for 15 minutes. So it is 7 past 11. So let's get back 20 past 11. So the question is asked by Frank. In mediator topology, system can handle complex situations whereby even errors are minimal. So what causes mediator to send an order or command to human interaction? So Frank is probably referring to this hard event mediator, that we have. So we can have a business process management engine like JBPM that can support human intervention. We need to consider the possibility that sometimes systems can be really safety critical. So we want to have some kind of human intervention if something goes that we did not, plan. Like it could be a system, like let's say flight information system. Imagine we are in this, what are they called, the people who control all the flights, which one should be land proper, which one should land and which one should take off. So it's a really, really complex system, a lot of hundreds of people controlling it, a lot of communication happening between tower, between people on ground, and between the aircraft, flying pilots. So in that scenario, it's really important to see all the system visible on some console where we can see, okay, our this control system is working and that control system is working and this one is working, so that with different lights, red light, green light, blue light, people are sitting there, engineers are sitting there all the time monitoring that system. Though we don't need monitoring, but because system will set off an alarm, there could be some light turning off and so on, but still the criticality of the system requires that there are people sitting in that control room all the time, so that if something that we did not think of beforehand may happen, which can we can switch off the system, we can restart it, we can do something on spot. uh, and for that kind of situation, this hard event mediator makes more sense. It would not you would probably not need that in an e-commerce application, But if you have that, it gives you an additional control as an administrator. You can always go there and see the things, and you can restart some of the components. You can, restart some of the process. So that is where this mediator topology can come in. Imagine you were in the middle of something, some process kind of did not get through, something happened. We saw some examples before. Something really, something happened, we don't know what, and we just need to restart, this shipping component. Everything is done. We examined the logs. A human examined the logs. Everything is completed, but the order is kind of stuck here. So we can go there and manually do it, or do, send this event manually so that shipping could be performed and things like that. In that situation, it makes sense to have this control through a human. Okay, now coming back to our current slide. Yes, so we were talking about the problem with asynchronous communication is how can we handle errors? Okay, synchronous communication allows us handling errors. If something goes wrong, we are waiting for that process to be completed. We have more control. But in asynchronous communication, we don't have that control. So what we can do to improve asynchronous communication so that we have much more surety that things will turn out as they should be. So error handling in asynchronous workflow. So the workflow event pattern, it's a pattern that you can implement within any asynchronous communication, and it can address the issues associated with error handling within asynchronous workflows. So in any reactive architecture pattern, so by the way, so event driven architecture is more like, a reaction. So an event is triggered and you react to it and you respond to that event. So asynchronous communication is kind of reactive architectural pattern that addresses the problems of resiliency and responsiveness. So you see the problem here, responsiveness was the main. Yeah, you got response back, but you did not know whether your comment went through or not. So responsiveness and resiliency. Resiliency means if your message did not go through, what can you do to ensure that it will go through? So resiliency in terms of error handling without an impact to responsiveness, that is very important. You want to keep the resiliency. That means errors are as low as possible. If some error happens, you want to still send or post that message. But you don't want to sacrifice the responsiveness that asynchronous communication gives you. Okay, so what it does, well, this pattern delegates. So delegate means, giving away your responsibility to someone. So this pattern leverages or depends on delegation. Someone else will do something for me. Containment, try to control the error, the damage of error that happened within the system, and repair, and then trying to repair what fault occurred within that asynchronous communication. So delegation is you ask some third party to do something for you. Containment is you try to control that, the effect of that um, uh, communication that did not go through. And repair is you try to fix it. So all these three things happens within workflow delegate. This is how it works. It works. So you got this event processor, you have an event channel, and you got this event consumer. So first of all, this could be post message, and this could be post message, and this could be process a message. So you just, when you click on post message from your side, through this service, a message is, or your comment is posted in the event channel asynchronously. It goes and then it is checked for errors. It checked for language, positive sentiments, negative sentiments, all that. And then based on the rules that you have, what kind of comments need, are okay to be published, you publish it. So that's an event consumer. You send a post and it consumes it and posts it. But now in the workflow event pattern, what you can do is you can add two more things. You got a workflow processor and you got a dashboard. Dashboard means human intervention. Okay. So let's see how it works. So uh, what happens, I want to see if I have anything here. No. So I have to go through it. Let's go through that slowly. So here, the normal flow of things is event producer puts something in the event channel and then event consumer consumes it, processes it. Okay. And if event consumer here experience an error consuming your post or message that you put in, when he or she, when this piece of consumer, it was processing your data, what it does, it delegates, it gives that error or message to this workflow processor, and then this workflow processor will try to correct it. And if it is correctable, then it will put back into the event channel. And when it's done, it will again be processed by event consumer. And if there is no fault, everything good. However, if the fault persists, so you send something, let's say it could be posting a comment, it could be some other transaction. Let's say now it is some kind of banking transactions or something important. You send it into the channel, on its turn, it is consumed or processed by this event consumer. There was an error in a format. Event consumer cannot solve it because there is an error. So it puts it into this event channel that will try to deals with it. So you delegate the handling of that error to this workflow processor. So this workflow processor try to look, parse that, tries to identify what is wrong, try to correct auto in an automated way. And if it is able to correct it, or it thinks it has corrected it, it will put back that transaction to this event channel. And then event consumer will again try to parse it or solve it or process it. If the problem is no more, then everything is fine. But if the problem persists, then it will go back to this event channel again. And the work processor will see that I tried to correct it before one time and I did not. So what it will do, it will put it on some dashboard for a human intervention. So it appears on some screen, it appears, some message within the system, and there is an administrator sitting there checking the system. He sees something, through SMS, or maybe a screen goes red, or some message appears, and then now through this dashboard, this human intervention will try to solve the problem. Once the problem is solved, it will be put back into the event channel and then it will be consumed by this event consumer. Okay, so this is how it works, delegation part of this. So we are trying to delegate and solve and then put it back into the channel. Through that, as you can see, the responsiveness is not impacted. Okay, on one post, on one transaction, it is. Now it is taking more time, but your system is not waiting. It is still asynchronous. All the processing is keep happening as it should be. And when an error happened, you give it to this and you keep processing new transactions. So your system is still responsive. And this one tries to solve the problem, puts back here, and then when it's done, it is processed, problem persists, comes back here, give to dashboard, and now an administrator, a human, will solve the issue. So that is how workflow event pattern looks like. So all that is written here that I just explained. And now here is an example I will try to give you. So yeah, imagine this is some trades happening. As you can see, the data looks like trades. So this is my account number or ID. And by the way, this is the data coming to us. So it's an account, a string value. Then we got side, buy or sell. Then we got symbol, AAPL, which share I want to buy. And then comes the shares. How much amount or price or whatever that is, I want to buy for. And then this is the format we agreed upon between this trading advisor component and or service and trade placement service. Okay. So all these messages will come here one by one, asynchronously, put it into this event channel. A message goes here, one message, and then when it's time, it is processed by the trade placement service. However, so it was fine for the first one, it was fine for the second one, it was fine for the third one, but it was not fine for the fourth one because I don't know, because of some reason, there it some text was also appended at the end, as you can see here. Now, when we strip it on commas, we got account easily, we got this symbol, we got this side and symbol, and but when we try to convert this value share into double or into float or into long, whatever that is, we get an error because now it is an alphanumeric value, 87756 space shares. So it cannot be, you got an exception here if it's Java or C sharp or Python. So then an error happened here. So on this message, an error happened. And then what the system will do, it will not stop. It will just delegate it to this channel. And when it's time, this workflow processor, which is error service, will try to programmatically solve this one. Like, as a system developer, you have seen what kind of errors in this system occurs. Like, you have seen that this thing happens frequently, or maybe some other patterns you identified. So you programmed here a piece of software that can, automatically, programmatically try to correct these kind of faults. So you try that script. So this workflow processor tries to fix that trade given whatever scripts you have written, your developer has written. If the problem, so now we don't know if the problem is solved or not, but we put it back into the event channel again. Let's say the problem is solved. Like we strip away these shares and we just have the numbers. So we pass it back to some double value or a float value or integer value, and it works. Everything good. So the problem is resolved. However, if it is not resolved, then in the diagram, they did not put it here. One more thing. If the problem still persists, you can remember this is counter number 2, that you are receiving this, share again. So you can just put it here and give it to your admin to look at it. And system keeps working as it should be. So these are the details, like, an exception can happen. You catch that this trades placement service was catching this exception, and in the catch block, you send it to workflow processor to solve that. So trade placement service cannot fix errors due to asynchronous, request here. So it has to be delegated to workflow processor. It kept going. I just explained to you the whole thing, how it happened. And now, like here, it tried to, your script tries to see that it has something that it should not supposed to have. It strips it away like that, and then puts it back in the event channel, and now it is processed. And then you receive, this message here in the log that trade is placed. So successfully trade has been placed within your system. We keep going, and then the problem in this kind of you need to think of is, what if the order of these messages are important? And usually in a trade, the order will be important. Let me see. I mean, I can't see anyone because this is an account. So I give you a scenario. Let's see. So I got this account number ACC123. That's my account. What I want to do is I want to place a trade to sell, and I am selling Microsoft. I don't know what ticker symbol they have, MSR, let's say. And then MF, maybe F, MST, Microsoft, yes. Okay. And then I want to sell my shares. I have 200 shares. And then it should happen first. And then with the same amount, that's my account, I want to buy from, let's say, Google. Let's say 100 shares, like that. So you see, I must sell first, and then only I can buy more. The order is important for me. So how we enforce order in this kind of setting where you are relying on it, you are delegating it on an error service so that your system stays responsive. So what you can do is there are many techniques you can use for such thing. One we discussed here, the order of the messages matter. Like you sell from IBM, that must happens before Apple. Okay, and then you buy from Apple. So what you can do is we can have, first of all, we can identify accounts. Okay, so all this, so let's say we have one more, then I do one more, then I buy AAP. Okay, so I sell Microsoft 200 shares, then I buy 100 shares from Google and buy 100 shares from Apple. Let's see, order matters here. So what we can do is for each account, we can have temporary queues. And in those queues, we wait for the faulty one to, so there we maintain order. So those are, queues with an order. Whatever comes first should go out first. So we can do that kind of thing. So what we can do, a trade with that same account number would be stored in a temporary queue for later processing, and it could be first out, first in, first out order. And then with that, uh, if there was an error here, let's say there was an error here, I will wait until, okay, this makes more sense if an error here. So this transaction is in a queue over here, and then it is waiting. This one is processed, but still it is waiting until we process this one and put it here. The rest of all accounts are going faster than, as before. It is only my transaction, since it got a fault, system fixed it and then restore the order of and keeps or remembers the order of my transactions through a temporary queue in a FIFO or first in first out way. So that could be the possibility. Then that was delegation, as you can see. Okay, and delegation is kind of supported by workflow event pattern. How can you prevent data loss? Another problem associated with asynchronous communication. Okay, it's a very common problem that you need to deal with when you are working with asynchronous communication. So there are like three places where you can lose data. So you got event processor A here, and then when you were placing it to this event channel, something happened, right? So you lost your data. It's no more. The event is gone. Or when you dequeue it from the event channel, it did not reach event processor B. Could be the communication problem, could be that event processor B becomes faulty, could, or like over here, it could be this communication channel is lost, could be because event channel is no longer available. Here it could be that this communication is lost, or it could be that this event processor is down because of some reason. And then the third place is when you want to persist your data on disk in kind of in some database or in file system. You want to store those records permanently. Here, maybe this database is not available, becomes faulty, or channel is lost. So these are three data loss options or possibilities or opportunities where data loss can happen. So issue one, message not reaching queue. Issue two, processor crash here. So it did not receive your message. Issue number three, database persistence failure. Here, because of some reason, the records could not be written in database. Okay, so event processor B is unable to persist data in this database due to some reason. We don't know what. So issue number one, let's discuss these issues one by one, and I will offer you strategies that we usually use. Number one, here, what you can do is, so first of all, what you can do is you can use synchronous send. And here you can keep a persistent queue. Let's talk about them. What is asynchronous send? It means that you don't just send and forget. No, you wait for an acknowledgement. That could be a synchronous send. Still, the distance, as you can see, is not too long. So your system will still be responsive. So you don't wait for the whole thing to be processed and written in database, and then that would take too long. Now you're just, ensuring that this message that you sent asynchronously to the event channel, it reached there. How you do that? You wait for a response from event channel saying that I got your message. Okay, that makes it a synchronous send. Okay, it is discussed here. Involves a blocking wait. You send a message and then you wait here until this event channel, confirms that I got your message. So it's a wait, but still small. The second thing is using persistent queues. What persistent queues means? Persistent queues means usually this event channel is in your random access memory. So if something goes wrong, everything is gone. No, you do two things in parallel. You have this thing in RAM, but also you write that dump in your physical memory also. You persist it. So this event channel is also dumped all the time on the disk in some kind of file system. Okay. So it's a now persistent queue. So now if due to some reason, some error happened here and this message is now lost, what you can do is, we will talk about this client acknowledge mode later. You can just restore, sorry, not here. If this event channel got lost due to some reason, becomes faulty, you can create a new event channel, restart it, and just load your previous state from the dump you put it on the disk. Okay, so that could make it persistent queues. So you solve two problems now with these persistent queues and with the synchronous send. So these, up to this point, your data is secure within asynchronous settings. Now let's move on now. Now you want to make sure that the message you send received is received by this event processor B. Same thing, what you do is you wait for an acknowledgement. So you are blocking here until what happens, you get back a response that with this client ID, we have received the message, and then you release it. So you wait for this one here also. Okay, this one, so this client acknowledgement mode will make sure if this one goes faulty, you sent a message, you did not get back acknowledgement, you will not dequeue this message. You will keep it until the event processor is back. You start from the same message again. Okay. And then the third one is here, last participant support and ACID transactions. So we will talk about ACID transactions. What ACID transaction is, everything should happen in the database in a persistent way as it should be. The ACID properties that we have already covered in our previous lectures. So what should happen is that event processor, once it has finished the processing, and it wants to write those updates into database, it does not throws away the records here. It waits it to be persisted on the database through this transaction. Okay, through commits. When commits really happens, then it wait for the whole thing, the whole transaction to complete. The first thing is persisted, second, third, and the last participant, when it also got back here, persisted, and then you get back a confirmation, then you simply remove them. So this is called last participant support, or LPS, removes the message from the persistent queue by acknowledging that the processing has been completed and message has been written in the database successfully. So this is how we again guarantee that within asynchronous communication, our data is still saved, properly stored, and no part of it is lost. So with these three techniques. So now we come back to broadcasting capabilities. You remember in uh, um, in asynchronous requests, we don't need an immediate response from the event consumer. So, uh, so what is this request reply then? So in asynchronous request, we saw that, we don't require an immediate response from the event consumer. We can do many things, as we saw, three things at minimum we saw in the previous slides. But let's look at this scenario. What if you got an order ID that you need with ordering a book so that we can track it later on? Okay. Or you need some kind of confirmation number when you are booking a flight. So in event-driven architecture, you can have synchronous communication. Though by default, event-driven architecture supports asynchronous capabilities, but you can also have synchronous communication, and you can do that through request reply messaging, or we call it pseudo asynchronous communication. So it looks like asynchronous communication, but it is actually asynchronous communication. So let's see how it works. Here, so these are very critical things. We really don't want to lose order ID, and we don't want to lose, let's say, confirmation number. So we want to keep track of the whole process. We want to have that control, that an ID we have, we can really ensure that that whole transaction happened. So how we can achieve, we will try to see it through this example here. Usually in synchronous transaction, what happens, sorry, now this is asynchronous transaction first of all. So what you do is you send your message. Remember, it is pseudo asynchronous. So we will see what it means because it's kind of in the middle. So you send your request, whatever process you do, your message, you send it, and it goes into a request queue. And now, as soon as it hit request queue, okay, this process is now free. You can do something else. So control is back to your application to process more requests in asynchronous way. But then the process that was waiting here now is waiting here. So imagine you got many processes, one about my order, one about your order, one about a third person's order. Okay. My order is now in the request queue, and now I am waiting here for my order to get back. But system is responsive, so it will immediately take your order, and it will immediately take the order of third person, and it's keep taking orders like that. But all of us are now waiting separately in this reply queue. It is just like, buying a fast food from McDonald's or KFC. You go there, you order, you pay, and you get a ticket. And then with that ticket, you are now waiting on other side. We all are waiting. The system is really responsive. We go and immediately someone will serve us. They take our order. And when our order is being processed, of course, it takes time. We wait. We don't mind waiting when our order is being, processed. But it is that there is no line for me to order because the system is responsive. I go immediately, I'm being processed, and next one appears, and next one appears, and next one appears. This is what you can see in this request reply. So here you put your request in the request queue, and then you wait on another queue called reply queue. Okay, so with that you got two queues, a request queue and a reply queue. So you make a request and then wait on the other side on reply queue. So system is still responsive, and we have to wait for the processing. So I will now try to give you a complete example how it will really happen in request reply message setting. So here is my order, ID number 124, and CID or correlation ID is null for the moment. Okay, so I just come here, utilize make an order. I am assigned 124 as my order ID, and correlation ID is empty or null right now. It goes into the request queue, and now I am waiting here. How this reply queue will remember me? Through my correlation ID that will be assigned later on. So this request queue goes here, and then as soon as I am being processed, I am assigned a CID 124. Okay, immediately I know that my CID or correlation ID is 124. It can be generated, right? So you see how I remember that it is not something new. It is the same ID that has now become a correlation ID. So as soon as I make a request, I know my correlation ID. Okay. It is the same ID I started with. However, the even this is the one event processor, so it gave me an ID, and this is another event processor. It processed my request and gave me another ID, but it still remembers my old ID or correlation ID here. So this after processing is now put back into this reply queue. We got one correlation ID with 120, one correlation ID with 122 to be, get back. And now my one correlation ID 124 is now here. It has been processed and I was waiting for it. I fetch it. So this is what request reply message processing looks like using correlation ID. Now it could also be implemented through temporary queues. Request reply message processing through temporary queues. We can also do that. So the concept is that for each transaction or request, create a temporary queue. So here it looks like this. ID is 124, and at the same time you generate a temporary queue. So your queue is, or my queue is Q998, and it is placed in the request queue. It goes here. It is been processed. Once it is been processed, it got a new ID, and then it is placed. Now I don't need to remember anything here because I got my own dedicated temporary reply queue, and I was waiting to receive that at the other side of that queue. So it goes back here and given to me, and I received it. So this is how then request reply message processing will look like using a temporary queue. However, the problem is, as you can see, you are creating temporary queues. Imagine there is a lot of load on your system. You will generate a lot of temporary queues and then delete them altogether. Generate, use, delete, generate, use, delete. So it is very much simpler, but requires to create. So your message broker needs to create and delete these temporary queues all the time, which is fine if you don't have too much traffic, but it may slow down your system for large messaging volumes. So thus employing the correlation ID technique is often suggested for better performance. So this one would be much better for a high load and this one for a low load. So choosing between request-based and event-based. Now you got, these two, event-based and request-based. So both models are viable approaches for uh, software system design, but choosing the right model, is essential for your system to work well. So use, request-based model when your, uh, you know, when you have more data-driven requests. Those are well structured and providing you certainty and control over the workflows, such as, retrieving the profile of a customer data. And when you should go for event-based model, now when you say this request-based and event-based, I will take you back to the very beginning slide. I know we covered a lot and it can be confusing and we may, forget a bit. So this is the traditional request-based model. So what we are trying to say is that when you should use event-driven architecture or when you just go for more traditional architectural styles that we are more familiar with. So if you have well-structured data-driven requests where you prefer certainty and control over workflows, go for more traditional architecture, request-based models. But if you want more flexibility, you want action-based events, you need responsibility more, you want scalability, you want a dynamic system, complex and dynamic system when processing things, then you may want to consider event-driven architectural style or event-based model. So let us discuss, the trade-offs that event-driven architectural style provides you. It better response for dynamic user content. Scalability and elasticity is better. Scalability, you can simply, if one of the service is under pressure, scale that, only that part. Elasticity, the same thing. You can only need to scale some portions of the system. Better agility and change management. Agility, it's agile. Our payment processing system needs to now support Swish instead of, a credit card. Well, it's just one sprint you go through, you patch it up your payment processor, and you have an agility. Every other thing within the system, all other event processors or services are working as they should be. You don't touch them, you don't change them. You just change whatever is needs to be updated. So change management is easy. Agility, you got better adaptability and extensibility, same reasons. It's more extensible. You really have, improved the business process, requiring more services, requiring more kind of processing. You just extend your existing system. Real-time decision making requires better real-time decision making and better reaction to situational awareness. However, it only supports eventual consistency. You are and we learned few things how we can still make our system consistent. Less control over processing flows, we saw that. Less certainty over overcome of event flow. I mean, if something goes wrong, how certain you can be to control the chain reaction happening in broker topology. You have less control. Difficult to test and debug the whole thing. Okay, let us look at the architectural ratings. First of all, event-driven architecture is technically partitioned, where domains can span on multiple event processors via mediators. For instance, you remember mediators? You can have mediators, you can have queues, you can have topics. So it can be a layered technical partitioning. And then you can have number of quanta, one to many. And when we say one to many, of course you have many services or event processors. So if two event processors are really close to each other, they can be in one quantum, or if they are really different from each other, domain based and the way you code it, it could be two quantums. Though the whole communication is still asynchronous, but given that two things are functionality wise really close to each other, you can still consider them one quantum. So here is an example, like for instance, imagine, so this is an example of one quantum. Quantum also can mean, really the strong dependency on each other. So imagine you got one event processor, one, depending too much on event processor two. You can't really go to event processor two until event processor one actually processes an event. Now what you do, EP1, waits for the order ID to come back from EP2. So one depends on another. Now, because of this dependency, though it's an asynchronous setting, though those are two components, you can still consider it as one architectural quantum from the functionality point of view because of too much dependency on each other. Then, as you can see that fault tolerance, evolutionary, modularity, performance, and scalability. So 5 stars are for evolutionary, fault tolerance, performance, scalability. No wonder we have seen that. However, if you look at simplicity and testability, it's not a simple system, as you can see. It's really complex and hard system. And it would not be, it would be really expensive to have it overall cost like 3 stars. It's not a simple system and testability is also kind of hard. But all others, as you can see, like for instance, yeah, deployability and elasticity, 3 stars. Overall cost 3 stars because it is still expensive. Elastic, it's elastic, but not as much as some other systems or styles we will learn in future. Deployability is hard. Okay, pretty good, but not 5 stars here, and so on. So that was our event-driven architecture, and we are almost running out of time. We have time until 15 minutes past 12. So what I plan to do is I just introduce to you some of the, basic few slides, and then we build upon further in the next class. Or I think, okay, we can just stop here today. We covered our event-driven architectural style, which was a huge topic. So let's focus only on that. So with that, I think we can stop the recording. And if you have any question, feel free to ask me.